Welcome to another video. In this video, we're going to talk about inverses. So we're going to discuss when functions have inverses. We're going to discuss how you find inverses, how you can tell you found inverses or that two functions are actually inverses, and what they look like once we found them. So kind of the graphs of inverses. And again, remember why we're doing this. The whole reason why we're talking about inverses is because we want to get to exponentials and logarithms and discover that they are in fact inverses. We're going to do that very, very soon. And that's very powerful for us. It lets us do a lot of different sort of things mathematically. So let's talk about inverses, where they come from. What an inverse comes from is from something called a one-to-one function that we talked about in the last video. So here's something you need to know. If a function has an inverse, it's going to be one-to-one. And if a function is one-to-one, it's going to have an inverse. And that is exactly what this first statement says. A function has an inverse if and only if it is one-to-one. That statement, if and only if, is kind of strange if you've never seen it before. That's called a biconditional statement. It means one is necessary and sufficient for the other. In other words, it says, if a function is going to have an inverse, it's got to be one-to-one. And if a function is one-to-one, it's going to have an inverse. It basically goes both ways. So inverses are important and one-to-one functions are important. You can't have an inverse without being one-to-one. And so we needed that. We needed to understand that functions were one-to-one in order to have an inverse. A couple of the things I want you to know when we talk about what an inverse is. An inverse undoes something. So like addition and subtraction are inverse operations, and likewise, inverse functions are going to undo each other. And we're going to talk about that when we get to the composition here in just a minute. A couple other is that if f of x is a one-to-one function, which means it's going to have an inverse, right? If we know it's one-to-one, it's going to have an inverse. Then we have a little notation for that. And we can say a couple different things about being about being an inverse. A couple different notations. Typically, we're going to see this little -1. And in my opinion, it's really not great notation. Usually, it's a little bit better to use something like arc or inverse and just say it, but this is the notation that we have. And so when you see that, it is not an exponent. What that stands for, it's not f to the -1 power. It's not a reciprocal, because it would be a reciprocal. It would be 1 over f of x. That's not how we find hardly any inverses. What that means is, and how this is pronounced, is f inverse of x. So for a one-to-one function f, and it's going to have an inverse, that inverse function is notated as f inverse, and it has a little -1 as a superscript. So the inverse is f inverse of x. That's how you say that. And it's also going to be one-to-one. And that just makes sense. If an inverse is if a function is one-to-one, its inverse is also going to be one-to-one, because, and we're going to find this out, essentially we're just switching x's and y's to create our inverses. So we're going to get into that in just a little bit. So recap real quick. One-to-one functions have inverses, and inverses have to be one-to-one. They're going to undo each other. We're going to see that in just a second. And then if a function is one-to-one and has an inverse, it's going to, we write that as a superscript with a -1, and we say f inverse or g inverse or whatever the function's name is. So what is this whole undoing thing about? When you have a function and you compose it with its inverse, for instance, when you have a function f and its inverse and your input is x, here's what the undoing says. We saw this when we did composition of functions a couple videos ago, that we actually had an inverse. And what happened was we took an input, we ran it through a function and another function which was its inverse, and it gave us back the input. This is what this is about to say. If you take an input, where would this go first? This would go into the inverse function, and then the output of that would go into the original function, this f of x, and it would give you out whatever you plugged back in. Well, what did you plug in? You plugged in x. If you compose a function and its inverse, it's going to cancel out all the operations, everything about it, and it's going to leave you with whatever you plugged in. That is what an inverse function does. And so here we'd say, all right, our input is x, it ran through one function, and the inverse of that function is going to undo everything about it. The inverses undo each other. It's going to leave us with x. What if I did it the other way around? What if I ran my input through the function and then that through the inverse of the function? It's going to leave you with the same thing. This is the only time in the world that when you compose functions differently, when you switch them around, like commuted if you want to think of that. If you compose two functions and you reverse it, and you compose those functions the opposite way, and you get the same thing out, it says those things are inverses, and the thing you will get out is x. I hope it makes sense that that x that you're getting out is your input. If you plugged in 5, you get out 5. You plugged in -2, you get out -2. By doing this, why? Well, because when you plugged into your function, it did something to that input, right? It gave you an output. But then if your inverse undoes everything that it did to that input, it's going to give you back the input. So it's going to undo everything the function did. Likewise, the function would undo everything the inverse did. They are inverses of one another. We're going to see that in a couple of these examples. I'll show you that. Before we get into it, I simply want to show you with one example on how to find an inverse of a function with just some points. So before we get into this one, imagine that we had just this relationship. And I say, I want to find an inverse for this. And this is going to lead us on what to do with these algebraic functions that we have on the board. Firstly, we do need to understand what one-to-one means. So one-to-one means, number one, that it is a function. That means our inputs, 1, 3, 7, and 5, can't be repeated. And it has to be one-to-one function. Our outputs cannot be repeated. -2, 5, -3, and 8. This is a one-to-one function. It's a function because every input is giving us one output. We can see that. And it's a one-to-one function because not only is every input giving us one output, but those outputs are unique. Every input is giving us one unique output. Those outputs are not repeated. So here's what an inverse would do. Think about the work behind it. And this is going to illustrate why this happens. Think about the work behind it. So if I plug in 1, what my function does, my function gives me out -2. What would an inverse have to do to undo all that? It's going to have an inverse because this is a one-to-one function. It has to have an inverse. But what would happen? Well, if my function is mapping basically 1 to -2, then the inverse has to undo that. Where is the value now? So if I plugged in 1 and got out -2, I went from 1 to -2. The inverse has to say, well, wait a minute, I got to take that -2 and I got to move it back to 1. I have to undo everything about it. I've always thought of this because I got some kids like 2-year-olds. When you're trying to clean the house, this is like a 2-year-old. So you take toy and you put toy on away. Let's say this is like the toy chest or something. You take toy from floor to toy chest. What's 2-year-old do? Immediately, right after. Toy chest to floor. Yay! That is what an inverse does. 2-year-olds are cleaning inverses. They undo everything that you've just done. Well, that's true. 1 to -2 got undone. Now it went from -2 back to 1. Notice what happened. It took my input, ran it through a function, ran that output as an input through an inverse, and gave me back what I'd originally plugged in. So I plugged in 1, I ran it through function, inverse, and it gave me out 1. That's what this says. It says take your input, run it through function, run it through inverse, get back out your input. Take input, run it through function, run it through inverse, get you back out whatever you plugged in. That's all there is to it. Every point we can manipulate that way. So our inverse is going to say, all right, what are you doing really? In essence, all you're doing is you're changing your input and your output. You're just swapping them. Your input becomes your output becomes your input. So the inverse of 3, 5 would be the point 5, 3. And for 7, -3, that inverse would be -3, 7. And finally, 8, 5. This would be the inverse of f. We call it f inverse. And all we're doing essentially is switching our x with our y. That is what inverses really do. And that's how they undo the function. They just say, all right, well, hey, you took an input and moved it to an output. I'm going to switch that. I'm going to take the output and move back to an input. It should make sense. It's just switching your x with your y. It's replacing those or reversing those. So that's a bit about why this works. One illustration of that. We're going to see that now as we solve for these functions for inverses. So let's get started. Let's take a look at f of x, 1 minus 3x. I'm going to give you a series of steps on how you can solve a one-to-one function for its inverse, how you can find that. The first step is if we're going to have to switch x with y, and that's exactly what we did in the previous example. We just switched the input with the output, or the x value with the y value, and it gave us an inverse. We're going to do the same thing algebraically, but we don't have a y. We do have something that stands for y. f of x, h of x, g of x, those are all the output value. Those are all the output for your function. And we can call that y. F of x, g of x, and h of x are just a little hard to work with in some algebra. And so we're going to replace that with y. So step number 1, replace your name of your function, f of x, with y. Step number 2 is you're actually going to find the inverse right now. You can perform that. Performing the inverse is exactly what we did earlier, switching your x with your y. And we're going to do that. Every place we see y, which should only be one place. Remember, there's only one output, right? So you should be just one place. We're going to call that x. And every place we see x, we're going to call that y. In this way, we have just reversed the input and the output. This right here has done the inverse. What we're going to do now is solve for y. Why? What's it going to do? Notice if I replace my output with an input and an input with an output, and I solve for this, it's going to have to undo everything about this function. It's going to undo all these operations. It's going to undo the function itself, and that's what an inverse does. It undoes a function. And so we replace with y, we change our y to an x and all of our x's that we have into y's, and then we solve for y. It's not going to be that bad. We're going to subtract 1, divide by -3. I really don't like seeing a negative on the denominator, so I'm going to write this a little differently. Maybe move my negative to my numerator, in which case you would have to distribute. And this essentially is your inverse, but you want to call it such. You want to say, yes, this is what I've done. This is the process of finding the inverse. I've replaced it with y, so I had something I could work with easier. That's the only reason why we do it. I've replaced my output with an input with an output, and I've solved for y. That's undone the entire function, but then you're going to call it that. So you say, this process will find you the inverse for any one-to-one function. And then what we're going to say is, that is the inverse of f, so we're going to write it as f inverse. And that's really all I need you to be able to do. I need you to be able to take a function and find its inverse with the process that I've shown you. Now, let's take a look at the next one, g of x. G of x equals x cubed plus 4. We're going to say, all right, is that a one-to-one function? First off, is this a one-to-one function? Because you can only solve inverses for inverses if you do have one-to-one functions. So you go, well, how do you know? Well, it might be nice to take a look at those graphs. That's a line. A diagonal line with a slope of -3 looks like that with y-intercept of 1. So all of our lines are one-to-one functions. It's going to have an inverse. That's an x cubed. And there's no going back down on it. Because you've seen cubics go back down with some turning points. This doesn't have any because that's just a vertical shift of 4. Oh, wait, hey, all of our transformations are coming back at us. We should understand that. That's a power 3 cubic that has its original, before it was shifted, x-intercept and y-intercept is 0, 0. It's going through the origin, but it shifted up 4 units. It's not causing any additional turning points. This is a one-to-one function. And so we can now solve for its inverse. Since it is one-to-one, it's going to have one, and we go through the same process that we've just done. We're going to start by replacing our g of x with y. After that, we say, all right, if I want to find an inverse, I'm going to have to undo the function somehow. I've seen some teachers teach it like, hey, just solve for x. You can do that. And then switch your variables, but I've seen a lot of students accidentally leave it in terms of y, which is, we don't want that. So instead we go, all right, well, what can I do differently? I could change my output to an input, and my input to an output, or in other words, switch y to x and every x to y, and then solve for y. And it accomplishes the same thing, but it's a little bit more understandable, and what you get is going to be your final answer. You don't have to switch all your variables after that. So let's solve for y, and in doing so, undo our original function. We're going to subtract 4. And lastly, how we get rid of a power 3 is with a cube root. I'm going to ask you something that should pop into your head really quick. When you take a cube root, do you need to put a plus and minus in front of your cube root? And you should know that. You should know with a cube root or a fifth root or a seventh root or any odd root, you do not need that. Because power 3's maintain the sign of their radicand. In other words, what's on the inside, if it's negative, you maintain a negative. If it's positive, you maintain a positive. You don't need that. Power 2's, what happens when you take a square root? Well, with square roots, you would need a plus and minus, wouldn't you? So if I needed a plus and minus, because those even powers, 2, 4, 8, 6, if I square a negative, it becomes positive. It does not maintain the sign of its radicand, which is where that came from in the first place. I don't need them for cubes or cube roots, but I certainly need them here. We're going to talk about that in a second. So if we simplify, we know that this is going to be y equals the cube root of x minus 4. That is the inverse, but I'm going to say that this is the inverse. One thing, man, you're going to see this all the time, a lot of the times. Because our notation is based on having a function f, because it's very, very common, many times you are going to see this. And this is technically incorrect. It's just actually incorrect. When you call something an inverse, you need to say what it's the inverse of. So if I use f inverse, I'm not really matched up with the original function that I'm finding the inverse for. So if I find the inverse for g of x, it's not going to magically become f inverse of x. We're going to call this whatever the name is, inverse. So this is the inverse for the function g, not f. So in both cases, we replaced with y, we replaced our y with x, x with y, we solved for y, thereby finding the inverse, and we've called it an inverse. Now, what is that for? Well, that essentially tells you what's going on. It tells you that you're undoing everything, and that's exactly what we've done, but it's also a way for you to check your work. Here's how. If you compose what you get here into what you get here, or what's here into what you found, what's going to happen is these two things will cancel everything out and you will end with x. Why? Well, if your input is x and a function and an inverse undo each other, then the output also has to be x. It has to be whatever you had originally. It's got to not essentially do nothing. You start with x, you end with x. So we're going to show that. We're going to show this in this example that when you compose a function with its inverse, in either way, it's going to simplify down to x. So let's try it. If we want to check our work or check whether any two functions are inverses, just compose them. It doesn't really matter the order in which you go. Whether you want to do g of g inverse or g inverse of g, it doesn't matter. Sometimes you're asked to show both. That really doesn't matter, because if you do it one way, it's going to work both ways. So let's check g inverse into g. If you remember compositions, this is why we did compositions. Everything should be coming together right now for us. If we do compositions, we look at our first function, this function right here. We say, let's open that up with a blank space. Take the second function, which is what we have right down here. Evaluate it, essentially. Just plug it into the variable or the blank space of the function you just opened. Now, it doesn't have to be this easy. This is the easy one because I wanted to show it to you. But everything should cancel. Hey, cube root to the third power is gone. X minus 4 plus 4 is x. This is what will happen every time you compose a function onto its inverse or an inverse onto its function. Every time. In fact, if you wanted to picture this, just think about it. If I did the opposite, and I took this function and put it here. So this x would be x cubed plus 4. X cubed plus 4 minus 4, those are canceled, you get x cubed. The cube root of x cubed would be x. It'd give you the same exact thing, no matter what. And that's what compositions of inverses do. Where are we going with it? Like, why? Who cares? When we get to logarithms and exponentials, we're going to find out the following things. We're going to find out that an exponential is 1 to 1. Well, that means it has to have an inverse. But none exists in what we had. And so we created one. We discovered one, however you want to think about that. We discovered logarithms. Okay, exponentials and logarithms are now inverses. What's that mean? It means when you compose them, they're going to cancel. That's exactly what this says. If you compose a function with its inverse, it's going to cancel. If you compose a function with its inverse, it's going to cancel. We're going to discover that logarithms and exponentials are inverses, and therefore when you compose them, they cancel. And that leads us how to solve exponentials and how to solve logarithms. That's why we need it. That's why we did compositions to get to one-to-one and inverses so that we can explore exponentials and logarithms. That's why. All right, let's talk about the last one. H of x equals x squared plus 9. And you are asked, find the inverse of this function. Maybe even find it and verify that they're inverses by doing a composition. Sounds like a lot of words. It's not that hard. However, you do know something about inverses. You know that they have to come from one-to-one functions. Well, think about that. This right there is a parabola. Are parabolas inherently one-to-one? Well, no, they're inherently not one-to-one functions. There are many outputs which are repeated. There are many equal outputs that give us different inputs. Here's what happens if you try to go ahead and find an inverse of a non-one-to-one function. You're going to run into a situation that as you're solving this for y, you're going to be having one input give you two different outputs. We're going to see it in here. So here's how to fix that, or how textbooks or teachers fix that. They say, okay, is that one-to-one? Well, no. Can you find an inverse of something that's not one-to-one? No. Every single inverse has to come from a one-to-one function. So how do we fix this problem? This is a parabola that is shifted up 9 units. So if I just look at one side of my graph, so either the positive x-axis or the negative x-axis, well, then it becomes one-to-one. So I find out where that axis of symmetry is, and I say, well, let's just take a look at that. Let's take a look at when x is greater than or equal to 0. Well, then at that point and further to the right, this would become a one-to-one function. This is a parabola shifted up 9 units, and I'm looking at just where x is positive. It's going to give me that half of a graph. Oh, is that, let's say that's 9. Is that one-to-one? Yes. If I ignore this other half of the parabola, if I ignore that, and I say I am ignoring it, if I ignore that, then that is a one-to-one function. And in order to find that inverse, we can go through the same process. But you are going to see that when we start solving this for y, we would, unless we had done that, we would come up with a situation where one input would give us two outputs. This is the whole reason, and do not miss this point. The whole reason you needed one-to-one was so that one input gave you one unique output. Why? So that when you switch them, like we do, we switch x's and y's, then that output becomes your input. So what that says is that if I have two inputs giving me the same output, remember my output is going to become my input. Then I'd have one input give me two different outputs. That would be a non-function. This is why it was so important for us to have a one-to-one function. So one input, one unique output, not repeated by any other input. That would be an issue. So I switch it. That's not even a function anymore. So let's solve this. Let's see what the issue would be. The first thing that we're going to do is we're going to set our h of x equal to y. So basically we replace it with y. Gives us something that's a little easier to work with. Then we're going to replace y with x and x with y. We're interchanging our outputs and our inputs. And as we solve for this y, as we solve the output, it's going to undo everything about this function. And it's going to give us our inverse. So let's subtract 9. And here it is. When you took a cube root, you didn't need a plus and minus. But when you take a square root, fourth root, and even radical, when you do that on both sides, yeah, for sure, you're going to have a plus and minus. And let's check this out. Think back. I really need you to think back to one of our first videos, and we discovered functions versus non-functions. And we said, all right, if you have a plus and minus stemming from the fact that you were taking a square root of both sides, you had a non-function. That's exactly the point I'm trying to make here. This is not one-to-one. This is not one-to-one. Without this, this is not one-to-one. If you go and try to solve it, if you try to find an inverse of a non-one-to-one function, what you're going to get is a non-function, period. If you plug in one number besides 9, plug in one number here, it's going to give you two different outputs. One input would give you two outputs here. That's a problem. It's not even a function. Why would one input give you two outputs? Because two inputs here gave you the same output. So if two inputs give you the same output, one new input, that's your output, would give you 2 new outputs. You're switching them. This would not even be a function anymore. So how do you fix it? You fix it by restricting your domain. You fix it by saying, okay, we're only looking at this part that is one-to-one. What that would be is, now remove that negative. If our x is positive, it would give us just those positives there. And that's the way we get around this idea of, if you don't have a one-to-one function, can you still find an inverse? No, but you can restrict your domain so that that changes the function into being one-to-one, or looks at just the one-to-one part of that function. So this came from h. That's h inverse, and we say that's just the square root of x minus 9. If you needed to prove that that was the inverse, you would show a composition. I showed it this way, I'm going to show it one more time. I'm going to show it backwards just to show it the same thing. So if I compose my first function onto my second function, or my original h of x onto the inverse, I'm going to open h of x, h inverse of x with a blank space. I'm going to put my function inside. And we can really easily see that all this stuff's going to cancel. A function and inverse they into each other. If I start with x, I'm going to get out x. And that happens every time when you compose inverses, and that's how you check. We're going to come back with a few more examples, a little bit more robust, I'd say, and then we'll be done. Let's get after it. We got 4 more examples. We'll talk about the graphs of inverses, how they look. It's going to be very important for exponentials. And then we'll call it a video, and we'll move on to exponentials in the next video. So I'm going to run through these fairly quickly. The idea is not for me to teach you more about inverses, where they come from, but to show you some of the techniques you need to solve for y. There's some factoring involved that sometimes students just forget that you can do. And so I'm going to show you that. It's very useful now. It's also very useful when we solve for logarithms in about a lot of videos. So let's take a look at them. Number one thing, when you get these examples, it's going to say, find the inverse for this one-to-one function. So you don't necessarily need to check for it. The times when you see really that something's not one-to-one is when you start having to take a square root. And you go, oh, wait a minute, that's a problem. And therefore you need to restrict the domain. We'll see that right here. Like that's an even function. We'll talk about that. Even functions are symmetric about the y-axis. We need to restrict the domain. But in general, you go, all right, that's one-to-one, because it's going to tell me that. Well, I can test it out like we've done before, but in general, those are going to be one-to-one if they're asking you to find an inverse. So that's a one-to-one function. You could graph it if you wanted to. I taught you how to graph them, but it's for sure going to pass the horizontal line test. That's one-to-one. So we're going to run through it. I'm going to show you all the techniques that you need. Number one thing, you're going to replace your output with y. Then what we're going to do is replace the y with x and replace every x with y. And finally, we're going to solve for that y. Sometimes it's not all that easy. Sometimes it is. It's not that bad. But in general, that's our idea. So if we solve for y, we're going to have to somehow move y off a denominator. You can do it a couple different ways. You can picture this as a proportion and cross multiply. If you think of this as x over 1, that's totally fine. You can multiply both sides by the denominator. That's okay too. That's what I'm going to do. You can just switch this with this denominator, which is eventually what we're going to do anyhow. And so I'm going to show that to you. So let's multiply by 2 minus y and 2 minus y. What are we going to get? On the left-hand side, we get 2 minus y times x. On the right-hand side, we get 4. Now, here's what I'm going to tell you. At this point in a lot of these examples, it's time for you to make it the correct choice. You either distribute or you don't. Here's how to tell. If you have all of your y's already on this side in parentheses, just divide by that x. If you don't, then you need to distribute. Collect all your y terms on one side, all your non-y terms on the other side, and you're going to factor. We'll see that in a couple examples. But for right now, if we look at this and go, all right, I've got all my y's right here. I am just trying to solve for y. There's no other y's anywhere else. I do not need to distribute. If you do distribute, is it a problem? No, might be a little extra work, but it's not a problem. So we're going to divide by x. We're going to subtract 2. And if we divide by -1, we get y equals, I'm going to switch our order here, +2 minus 4 over x. We're done. That's our inverse, 2 minus 4 over x. If you have to make this one fraction, remember you need a common denominator. That'd be 2x minus 4 over x. You can do that. X over x. And that's fine also. It's the same exact thing. And you say, all right, this is f inverse of x. Okay, what if you don't like that? What if you don't like the divide? What if you say, you know what, I'm just a distribution kind of person. I just love distributing. That's fine. There's nothing wrong with that. In fact, we're going to do that on all the rest of our examples. We're going to have to distribute that. If you do distribute from here, so we not divide by x, if you distribute, then at this point, collect all your y terms on one side, all your non-y terms on the other side. And then, if you have more than one y term, factor the y and divide. If you don't like here, just divide. Just divide by -x. We rarely like to see a negative on the denominator, so I'm going to take that, run that through the numerator. So if I divide by -1 on the numerator and denominator actually, I would get 2x minus 4 over x, which is exactly the same thing that we got. Either way works. Pick the way that you're most comfortable with. A lot of people actually do like the distribution because they're used to it. I'm just saying you don't really have to do that. You can divide. The main point is collect your terms with y's, factor if you have to, and then your final step should be divide. Maybe change your signs. And that's our inverse. Could you compose it? Yeah, you could, but you'd have to take this function and put it right there. If you did that, you need to clear a denominator, but it is going to eventually cancel out everything and give you x. All right, so let's try g of x. So g of x equals -2x over x minus 1. We're going to get right after it. We're going to try to find the inverse. So let's replace our g with y. Every place we see y, which is only one place, we're going to change that into an x. Every place we see an x, we're going to change that into a y. Now, we've got to solve for y, but we also have a denominator, so we're going to multiply both sides by that. And we end up getting y minus 1x equals -2y. In the last example, I gave you that example to show you that it's not always necessary to do distribution. However, if you ever have a y anywhere else beside in that parentheses, you have to distribute. The idea is get all of your terms with y on one side, all the terms without y on the other side. Why? Because then you can factor the y and divide. And that's what we're going to do here. So when you see this, if you're confused, just distribute. We know that it actually does work. Both cases are going to work. But here, for sure, you're going to have to distribute this. So when we distribute, we get xy minus x equals -2y. And this is where a lot of students get stuck. They go, what in the world do I do now? Because I have y's in two different places, what am I going to do? Factor. But in order to factor, you get your y's on one side and non-y's on the other. That way every term has a y in it. So I'm going to take this and move it over here, and this and move it over here by adding x on both sides and adding 2y on both sides. So that's what we're doing right now. I'm going to add 2y to both sides. I'm going to add x to both sides. And look what it does. If I collect my terms with y and separate my terms without y, it leaves me every term with y over here as something that has a GCF of y. I can factor. Looks like magic almost, like, oh, that's cool. I've just changed 2 y's into 1. Well, that's what factoring does, doesn't it? It removes it from all the terms and puts it in one spot via multiplication. But now I can divide because it is multiplication. And that right there is the inverse of the function g that we started with. You can check your work. You can compose it. It just becomes more difficult with some of these harder problems, more complicated, because you have to plug in this function in at least 2 different places most of the time. So you take this, plug it in here and here. You'd have to simplify that complex fraction that you're going to get with the LCD of x plus 2, distribute, combine some like terms, factor, and it's going to cancel out and leave you with just an x. Just for fun, let's do it. So either way you go, it doesn't matter how you compose them. I'm going to compose g of g inverse. So how compositions work. You open up your first function list. As I'm looking back at my g, I'm going to replace all my variables with some blank spaces. Into those blank spaces, I put my second function. So into this function, I put this entire function. So into my blank spaces, I put this, what I found. Now that's kind of nasty, but this is the reason why we deal with complex fractions in like an intermediate algebra class. It's so that we do this. So how do I deal with complex fractions? We multiply by the LCD. So our LCD here is just x plus 2. We're going to multiply both the numerator and denominator so as to multiply by a really fancy one. Equivalent rational expressions is what we're creating here. I'm going to multiply both the numerator and denominator by x plus 2. On this numerator, that just cancels, and that's great. So on this numerator, I'm just going to get negative 2x. On my denominator, keep in mind, you have to distribute this. So I'm going to distribute, yes, it's going to go here, x plus 2 and x plus 2 are going to cancel. I'm going to get x, but it also multiplies to the 1. Now, when you multiply by 1, you're going to subtract that whole thing. So what's that look like? Oh my gosh, I'm subtracting the whole thing. I'm subtracting 1 times that whole thing. So that's negative 2x over x minus 2, not plus 2. And because negative 2 over negative 2 is 1, we get x. And that proves it. That proves that these two things are in fact inverses. You can actually see it here too. Imagine plugging in anything but 1. Imagine plugging in something like 2. All right, so let's remember, we're plugging in 2 here. Plug in 2. If I plug in 2, I get negative 4 over 1. Well, that's negative 4. Now take your negative 4, plug it in here. Negative 4 divided by negative 4 plus 2. Well, this is negative 2. Negative 4 divided by negative 2 is 2. I got out. After I plugged it in and ran it through, I got back out 2. That's what inverses does, and that's what this composition is showing you. Okay, let's move on to the last two. Let's look at h of x, negative 3x plus 4. That negative is supposed to be out front. Negative 3x plus 4 over x minus 2. First thing we're doing to find an inverse is recognizing that it's going to be a one-to-one function if we're going to find it, or it has to have a domain restriction. So that's a one-to-one function. It actually has a horizontal asymptote at negative 3. That's what it's going to look like. But we're going to replace our h of x with y. And we show that every time. Now we take our y, we say I want that to be my x, and every place I see an x, I'm going to change that to a y. And now it's our job to solve for y. We're going to deal with something very similar to this, in that we're going to have to distribute and collect our y terms and factor. But we also see that negative. Make a choice with that negative. Do one of 3 things. Either divide right now by negative 1, and that's okay, you can do that. Or multiply through your numerator, which is what I'm going to do, or your denominator, which I don't recommend, but you can do. So I'm going to run this through my numerator and make this x equals negative 3y minus 4 over y minus 2. That way we have, at least we don't have a sign floating out front that we're not sure of. So you can always do that. You always just run it through your numerator. So I distributed negative 3y and then minus 4. Now we're going to go ahead and do our manipulation to try to solve for y. Let's firstly multiply both sides by y minus 2. And then we're going to check our problem. If all of my y's are right here, all I've got to do is divide. If I have more y's than are right here, I need to distribute, collect my y's, and factor. That's what happens here. So I have a y here and here. It says you're going to have to collect those terms. There's no way to do that without distribution. And now we see it. We got a y here, we gotta collect, and we gotta get everything else that doesn't have a y on the other side. So I'm going to add 2x and add 3y to both sides. Now we're ready to factor. Now because we factored, we have things that are multiplied together. We undo multiplication by division. We could check our work with a composition. Take this, plug it into the variables there, and simplify it. Yeah, you're going to get a lot of complex fractions, but it is possible to show that. And this is our inverse. So we're going to say that this came from the function h. This is h inverse. And that's it. I wouldn't say this is really conclusive, but if you did take a value besides positive 2, because you can't plug that in, and you evaluated here, took the output, plugged in here, and give you the same input, that's a really good indication without doing a composition that you have inverses. But really, to check your work, you're going to want to compose those. I hope this is making sense. I hope you're seeing the process, and the whole idea of why I'm doing this one is to make sure you're grouping your y's. That way you can factor it and not get stuck. Right there is where students get stuck on it. So let's come back. We'll do one more example. All right, here we go. So f of x equals x squared plus 3 over 3x squared. You go, wait a minute. That's an even function. Oh, I'll verify that's an even function. Even functions are symmetric about the y-axis. So if something's symmetric about the y-axis, no matter how it looks, it is not going to be one-to-one. So this requires something from us. If we have something symmetric with the y-axis, we can make a one-to-one part of it a lot of the times by taking and saying, let's just let x be greater than or equal to 0. Now, there's a problem with that too. In this case, we can't let x be greater than or equal to 0. Why? Well, it fails our domain. Our domain says you got a vertical asymptote on the on that y-axis. You can't let x equal 0. So we just want to be strictly greater than 0 here. I hope that makes sense. We put domain together with this hey, you have to have a one-to-one function. This section of the x-axis is going to cause this to be a one-to-one function. That's not normally something you would have to do. It's going to be given to you. It's going to say, hey, this is one-to-one, or hey, on this portion of the x-axis, this is a one-to-one function. Now find the inverse considering that. And so we go through that. So, all right, let's replace our f of x with y. Let's change our y to an x, our x's both to y's. And now we're going to solve for y. Do the same thing you did here. Let's multiply both sides by 3y squared. So 3xy squared, these are gone. You're going to get y squared plus 3. And now the same idea. Collect your terms that have y or y squared. And the ones that don't, leave them on the other side. So I'm going to subtract y squared. There's no distribution here. And then we're going to factor. Factor out the whole GCF. So factor out y squared. And now because we have factored, these are connected by multiplication, we can divide. and one more step and why that was necessary. If you ever see yourself taking a square root, you're going to normally have a plus and minus. If that wasn't there, oh man, I hope it makes sense. If that wasn't there, when you did this next step, you would have to have a plus and minus there. And that would create a problem for you because you'd say one input would be giving you two outputs, stemming from the fact that right here, two inputs are giving you one output. That would be a problem. So one input would give you two outputs if I reverse that. That's an issue. But because we restrict our domain, you don't have both. You just have the positive here. And that creates an inverse. And it's an inverse of this function on that domain. So what that means is that these are both one-to-one functions and they're inverses of one another. You can compose them. You might kind of see that your squares are going to cancel out your square root. Threes, you have a little bit of work with the LCD there, but it certainly would be an inverse. And we're going to say that this is f inverse of x. I hope I've made that make sense for you. How to find an inverse algebraically. So we've done it now with points, so we can just switch x and y. That's essentially what we've done here, just a lot more work. And we had to do it all the time, right? Because these aren't just 4 points, these are infinite number of points. So we can't switch an infinite number of points unless we do it with the function itself. And that's what we've done. We made sure to label it appropriately with our f inverse or h inverse, as the case may be. And now we're going to take a look at graphs very briefly to see that what a graph does from a function to its inverse. All right, last little bit. We need to talk about the graphs, and I hope you're still with me because this is really important. This is one of the ways that we're going to determine what a logarithm is from an exponential function. So here's what you need to know about a function and its inverse graphically. If this is our function, is it a one-to-one function? Yeah. Is it going to have an inverse? All of them do. All one-to-one functions are going to have an inverse function. Graphically, here's what happens. Because we switch our x with our y, you remember that we did with points, we did with algebraic functions, because you switch your x with your y, because your input becomes your output becomes your input, we are going to reflect our function across the y equals x line, and it is going to give us our inverse. So a function and its inverse are reflections about this y equals x line because we're switching x with y to create that inverse. That's the idea. So this function will look like this. Roughly. So if this point is, let's say, -3, 0, then now we switch that. If this was -3, 0, then 0, -3 should appear on my inverse function. If this was, let's say, 0, 4, just making these up right now, then 4, 0 should appear on my inverse function. And I've sketched this. This is approximate, but it's just to show you that this is the inverse of this function. The graphs are reflections about this diagonal line, this y equals x line. If you folded it, they hopefully match up. The distance here should be the same. And that's it. This is still a one-to-one function. They are inverses of one another. If I had this as our function, that would be the inverse. It doesn't really matter. They're inverses of each other. So moving on, what happens if you're required to graph an inverse from its function? I've given you one that I made up really quickly. So I've given you 1, 2, 3, 4, 5 points, one of which you notice is on that y equals x line. If we ever want to find the inverse, just take those points, reverse them, and reflect it about this diagonal line. It's a lot easier when it doesn't intersect that line to find a reflection. When it does, you're going to be crossing, it's going to get a little bit awkward. So here's the idea. If we have these 4 points listed, not that one, because that right there, if I reflect something on y equals x, it's going to stay y equals x. This is a point that's going to be on both of these functions, the function and its inverse. So if I have the other 4 points, then if -2, 1 is on the original function, remember that we're switching. That was not switching. We're switching the y with the x. So if -2, 1 is on the original, then 1, -2 is on the inverse. You don't change any signs, you just switch your x with your y. And 0, -1, -2, 0, and negative 7, 3. Let's double check. So switched, 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 and switched. If we plot those, 1, negative 2, that would be the new point for an inverse. 0, negative 1. This would be now this point for the inverse. This point is the same. Now my scale is a little off, but that's going to be the same. 0, negative, so negative 2, 0. This became that point, and negative 7, 3. This became that point when I reflected it. Now we're going to do our best to graph this. Looks about like that. This is a little off of our scale. But hopefully you get the point that all this is really doing is taking this and reflecting it about that point right there. Notice how they have to both have the same exact point, because that is on our y equals x. So I've taken this and I've just rotated it. And that's where it ended up. So I hope you're with me on the graphs. What we're going to do in the future is get an exponential and reflect it about that line. It's going to create the graph of a logarithm. We'll look at our key points for that. And that'll be about it. We're ready to get started on exponentials, which is exciting. A whole other world kind of opens up with us, or for us, with exponentials and logarithms. So at this point, you need to know that one-to-one functions create inverses, that inverses only come from one-to-one functions, and then how to find them algebraically and what they look like graphically. So hopefully it's making sense, and I'll see you for another video.